Okay, let's start the second and final part of the Thanksgiving review. And the next thing that we learned about was electron configuration. What is electron configuration? Go ahead and highlight this. Electron configuration, electron configuration is how the electrons are arranged in an atom. And so one of the things that helps us to understand and write electron configuration are orbital diagrams. And this is what I'm highlighting right now. Orbital diagrams help us to understand where the electrons and what orbitals they go in. And then we can easily write the electron configuration after we properly fill one out. But we have to understand the three rules of orbital diagrams. So the first rule is the Aufbau principle, and that tells us that electrons occupy the lowest energy levels available. So what does this mean? Well, let's take a look at our orbitals right here. We're going to start with 1s. That's what I'm highlighting in pink. And what you need to understand is electrons are always going to start with 1s. That's closest to the nucleus. Then after this orbital is filled, we're going to go to 2s, 2p, 3s, 3p, and so forth. We never start at, for instance, we never start at 3D, we never start at 4P. We always start in the lowest energy levels possible. And these orbital diagrams display the order that the orbitals go in. So rule number 2 is Hund's rule. And all this is saying that anytime we have a sublevel that has more than one orbital, that we need to, every orbital needs an electron of the same spin before an orbital can get a second electron. And then the Pauli exclusionary rule over here on number 3 says that electrons in the same orbital must have opposite spins. So if we're in the same orbital box, one electron has to have an up spin and the other electron has to have a down spin. Let's go ahead and practice filling out orbital diagrams to write the electron configuration of 3 elements, okay? First, let's do helium. All right, so helium, and you probably want to do this on paper, right? Helium, how many electrons does helium have? Well, go to your periodic table, atomic number 2, helium has 2 electrons. So what are we going to do? We're going to put 1 up spin and 1 down spin. Remember, in any box, the maximum amount of electrons are 2. So now we can go ahead and write the electron configuration using the orbital diagram. How do we do that? Well, we're going to start with our first, we just go sub-level by sub-level. So we're going to write 1s, and then there's 2 electrons in there, 1s2. And there is no noble gas notation for helium because there's not enough yet to do that. So we already did helium. Now let's go ahead and practice the orbital diagram for nitrogen. First of all, try to practice this on your own. You can go ahead and pause the button and try to work on that. Okay, the reason why I had you try nitrogen is because it's a common mistake that students make when they're filling out an orbital diagram. So let's go ahead and write nitrogen. Okay, we got nitrogen, and nitrogen has 7 electrons. If you go to the periodic table, you'll see nitrogen is number 7. All right, so let's fill out the diagram. We have 1, 2, 3, 4. Now, 5. A very common mistake that students will do right now is they will go ahead and fill out that first orbital, that first 2p orbital with 2 electrons. But you have to remember, this is a violation of Hund's rule. Hund's rule says that if we have more than one, a sublevel with more than one orbital, that first every box needs an electron first. So we have 5, 6, and then 7. So this is the proper orbital diagram for nitrogen. Now let's go ahead and write the electron configuration using what we've done. We start with 1s, and over here with 1s, I've got 2 electrons. Now we're going to go to 2s, and there's 2 electrons in there. Now we're going to go to 2p, and I've got 1, 2, 3 electrons in there. There's the orbital diagram for nitrogen. Now, noble gas configuration for nitrogen would be helium, and then 2s2, 2p3. Not very convenient. It's almost the same length, but you get the picture. All right, let's do one more practice filling out the orbital diagram. We're going to do it for sodium. And if we go, let's go ahead and write sodium, okay? Symbol is Na. And according to the periodic table, sodium has 11 electrons. So we're going to do, we always start with 1s, 1, 2, and then 3, 4, and 2s. Now, I know that I'm going to fill up all my 2p sublevel, but let's go ahead and do it properly, okay? So this would be 5, 6, 7. Notice how every orbital in that 2p sublevel, every orbital has at least one electron, and they're all the same spin. Now I can go ahead and for 8, 9, and 10, put the down spin on. I've got one more electron left, and it's going to be an up spin. Now I can just go ahead and use the orbital diagram that I've filled out to write the configuration. 1s, there's 2 in the 1s, 2s2, okay. I've got 2p6, because there's 6 electrons in that 2p sublevel. Now I can close it out and write 3s1. Noble gas notation, the noble gas that comes before sodium is neon. So I'm going to put neon in parentheses. And now I can just write 3s1. Now, orbital diagrams are one way to help us write the electron configuration. But when you take the ACP, we want you to use the periodic table method, because that's going to be the only method that you can use. And so try to understand the periodic table. All those orbital diagrams that you just filled out, they're arranged on the periodic table in order row by row. So here we have the 1s is here, the 2s is here. Then you go across the table, we've got 2p, 3s, 3p, and so forth, okay? So use the periodic table to help you write electron configuration. Okay, so here's a practice question. And I'm going to give you the example of how to do it. Write the electron configuration of sulfur. So step number 1, we want to locate the element on the periodic table. So I'm highlighting sulfur. Sorry, it's really late. I'm highlighting sulfur in pink. It is atomic number 16. So what I like to do is I like to write down the final destination. So I know that this final destination is going to be 3p1, 2, 3, 4. I'm going to end in 3p4. But what I have to do is I have to write every sublevel that's full until I get to that element. So we always want to start at hydrogen. So we have the 1s2 is that first row. Now I can go where lithium to beryllium is, and that's 2s2. Keep going across the table to boron, and this is the 2p sublevel. It's going to be 2p6. Now I can go to sodium and magnesium. That's 3s2. And then now I can close it out knowing that I am in the 3p4. So this is the proper electron configuration of sulfur. 1s2, 2s2, 2p6, 3s2, and 3p4. Okay, so here is a sample ACP question concerning electron configuration and orbital diagrams. What I'd like for you to do is correctly fill out this orbital diagram for oxygen and then write the electron configuration based on that. Okay, the second question is use the periodic table to write the electron configuration of manganese, not magnesium, by the way. So use the table to write the configuration of manganese, and then also it wants you to write the noble gas notation. So good luck with that. All right, so we are going to move to our next learning topic that we learned about, and it was about how to predict predict the type of bond that two atoms will form based on electronegativity. One of the most important things that we need to understand is metals and nonmetals. So, how do you know if an element is a metal or nonmetal? It has to do with its location on the periodic table. So I want everybody to look at where I'm highlighting by boron. This thick staircase line that I'm highlighting, that's the border about what's going to be a metal and a nonmetal. So I'm going to highlight all the nonmetals right here in light green. Okay, so these are nonmetals. I'm going to put NM. And then I'm going to highlight in orange all the metals. You can see we have a lot more metals on the periodic table. I'm just going to put M. And don't forget that hydrogen is a metal. So over here on the bottom, metals versus nonmetals, you're looking for that bold staircase line, okay? And that's going to be right where I drew the arrow right here, okay? Now, electronegativity is the most important property that's going to help us predict these type of bonds between the atoms. We had learned about the Pauling scale. So I'm highlighting this table right here. Every element is assigned an electronegativity number. And remember, electronegativity tells you how the ability of an atom to attract electrons in bonding. And what we've discovered, let's go ahead and fill this out on the bottom. Metals have an electronegativity under 2.0, generally speaking. And the nonmetals have an electronegativity 2.0 or above. That's going to help you to understand metals versus nonmetals. Okay, having said that, we need to understand the three types of bonds that can form between atoms. So we have ionic bonds are going to be between a metal and a nonmetal. That's going to be low electronegativity with high electronegativity. Covalent compounds are going to be between two nonmetals, so we have two high electronegativities. And then metallic bonds, it's going to be between two metals, low electronegativity and low electronegativity. Having said that, here's an ACP sample question. Good luck with that. Go ahead and pause the video and work on it. Then we have another ACP sample question. Good luck with that, and go ahead and work on that. Okay, so the next thing we're going to do is we're going to review the mole and Avogadro's number. And what we learned is the mole is just a word that represents a number. Just like a dozen represents 12 or a grand represents 1,000. A mole is, let's go ahead and fill this out, 6.02 times 10 to the 23 things. It's like a really big number, right? And the reason why we use the mole in chemistry is because atoms are too small and difficult to count. So we need to use the mole to easily work, and we have to be able to work with a bigger number in order to use them in the real world. So what is Avogadro's number? Avogadro's number relates the mole to chemistry. 1 mole is going to be equal to 6.02 times 10 to the 23 atoms, molecules, or particles. The next thing we have to understand when we're counting atoms is what we call the molar mass. So let's go ahead and fill that out. The molar mass is the mass in grams of 1 mole of any element. And this is going to be equal to its atomic mass on the periodic table. So when we're counting atoms and we're dealing with grams, we are going to need our periodic table in order to get the molar mass of an element. Let's look at our example right here. Let's look at iron. If I have 1 mole of iron atoms, we know that 1 mole of iron atom means that I have 6.02 times 10 to the 23 iron atoms. But how much does 1 mole of that weigh? Well, we go to our periodic table, highlighting it in green for iron, and we're going to pay attention to this number underneath its symbol, this 55.845. That's where we get the molar mass of an element. And we're going to need that when we're counting atoms and we're given grams. Okay, so here's an example problem, and I'm going to show you how I do it to help you. So we're reading this question, and it says the average pencil contains 0.167 moles of carbon. How many atoms of carbon are in the average pencil? The first thing that we always want to start with is our given. So we are given 0.167 moles of carbon, and we're going to put that over 1. Now, when we're going from moles to atoms, all we're going to do is we're going to multiply by Avogadro's number. But remember, what goes on the top on the other side goes on the bottom. So I'm going to do 1 mole of carbon. And for every 1 mole of carbon, we have 6.02 times 10 to the 23 atoms of carbon. Now we can put this in the calculator. And I've already done this just to speed it up. And we get 1.005 times 10 to the 23 atoms of carbon. And if we want to clean it up, moles of carbon cancel out because one was on the top and the other one's on the bottom. So we're left with atoms of carbon for our answer. The next question is going to involve grams to atoms. So let's read this question. It says the average oxygen tank to help people breathe contains 971 grams of oxygen. How many atoms of oxygen are in the average tank? First thing you always want to start out with is your given. So we're going to start out with 971 grams of oxygen, and we're going to put it over 1. Now, this is the step where students make their mistake, because what are they tempted to do? They're tempted to do what they did when they're counting moles to atoms. They want to multiply by Avogadro's number on the top and think everything's going to be okay. But we can't do that because we are dealing in grams. We're not starting with moles, we're starting with grams. And when we start with grams, in our second step, we're going to divide by the molar mass of the substance. In this particular question, we're dealing with oxygen. So we have to go to the periodic table and find the molar mass of oxygen, which is 15.999, but you can use 16 for oxygen. And we're going to put that under 1 mole of oxygen. Now we can multiply by Avogadro's number, because Avogadro's number is for every 1 mole of any element, I have 6.02 times 10 to the 23 atoms of that element. And if you put this in the Desmos calculator, you're going to get 3.65 times 10 to the 25 atoms of oxygen. And if we clean up our equation, grams of oxygen cancels out and moles of oxygen cancels out, and we're good to go. Okay, so here's an ACP sample question followed by another ACP sample question. So good luck working on that, and we'll see if you got it right when you come back. Okay, so the next thing we talked about was molar masses of compounds. And how do we calculate the molar mass of a compound? Well, we've got our steps right here. Step number 1, we have to count the number of atoms of each element in the compound. Then what we're going to do is we're going to use the periodic table to find the atomic mass of each element. Then we're going to calculate each element's contribution, and then we're going to add up all the numbers. So let's go ahead and calculate the molar mass of NaHCO3. So the first thing I'm going to do is I'm going to list the elements in the compound. I have sodium, hydrogen, carbon, and oxygen. And the next thing I want to do is I want to list how many atoms of each element I have on the compound. How am I going to do that? The chemical formula is going to tell me. So looking at sodium, there's only 1 atom of sodium, 1 atom of hydrogen, 1 carbon, and 3 oxygens. Now I'm going to put the molar mass of the atomic mass of each element from the table. Sodium is 22.990. Hydrogen, we can use 1. Carbon 12 and oxygen 16. Now this is step number 3. I'm going to calculate each element's contribution by calculating the number of atoms of each element by its atomic mass. So let's look at sodium. I have 1 sodium atom. 1 times 22.9 is 22.990. It's pretty easy, right? Hydrogen, 1 times 1 equals 1. Carbon, 1 times 12 equals 12. And oxygen, 3 times 16 is going to equal 48. So all we need to do now is, for step number 4, it says to add up all the numbers. So I'm going to add up 20. Oh, I made a mistake right there. 22.990 plus 1 plus 12 plus 48. The molar mass of this compound is 83.99 grams. And we're going to need this number. By the way, that's per mole of the compound. And we're going to need this number in order to convert from grams to moles. So the next thing you have to be able to do is you have to tell me how many moles are in a certain amount of grams of a compound. And here's the example. How many moles are in 93.89 grams of NaCl? So let's look at the steps. Step number 1, we got to calculate the molar mass of the compound. In this case, it's sodium chloride. Then we're going to divide the given moles by the molar mass. Let's go ahead and do this. All right, so the first thing, we need to calculate the molar mass of NaCl. Now, we learned how to calculate the molar mass of a compound in the previous slide. We've got sodium and we've got chlorine. We've got 1 atom of each, and we're going to multiply that by its atomic mass. Sodium is 22.990. Chlorine is 35.453. Any number times 1 is itself. So this should be fairly easy. And if we add this up, the molar mass of NaCl is going to be 58.443. That's in grams. But that's not the answer. We got to go back to the question. How many moles are in 93.896 grams? We always start with our given. So we're going to do 93.896 grams of NaCl. We're going to do it over 1. Now we can divide by the molar mass in step number 2. That's why we had to calculate it, okay? Grams of NaCl. And remember, the molar mass of a substance is for every 1 mole of that substance. So now we can go on the calculator, and we're essentially dividing 93.896 divided by 58.443. And when we do that, we're going to get 1.61 moles of sodium chloride. Now, if we really wanted to clean it up, grams of NaCl cancel out because one's on top and the other's on the bottom. But there's your answer right there. All right, guys, there is an ACP sample question. How many moles are in 100 grams of water? Good luck with that. The next thing we're going to cover is percent composition. Now, let's go over the steps for percent composition. Before I go over the steps, let's just go over the basic idea is that we're still dealing with compounds and we're still going to have to calculate the molar mass. But the idea behind percent composition is part divided by whole times 100. Now let's go over the steps. Number 1, we're going to calculate the total mass of each element in the compound, which are the parts. Number 2, we're going to add up all the parts to calculate the total mass of the compound. And then we're finally going to plug this into our equation, part over whole times 100, or the mass of the element divided by the mass of the compound times 100. Let me show you what I'm talking about. Here's our example. Find the percent composition by the mass of bromine in copper bromide, CuBr2. Step number 1, we have to calculate the total mass of each element on the compound. You guys are used to this. So the two atoms in this compound are copper and bromine. And according to the formula, there's one copper atom and two bromine atoms. Now we're going to multiply the number of atoms of each element by its atomic mass. Copper's atomic mass on the periodic table is 63.546. Any number times 1 is itself, so it's 63.546. Bromine, we have two bromine atoms, and the atomic mass of bromine is 79.904. So 2 times that is 159.808. We add the numbers together, and the atomic mass, the molar mass of this compound is 223.354 grams. Now, this is our whole part. Remember, we're going to need the whole part when it comes to this equation when we're calculating it. So I have my whole. What is my part? Well, my part is going to be the element. But what element are we talking about? Well, the question is saying bromine. So we already calculated the mass of bromine, and the compound is 159.808. That's my part. Now we can go to our formula, and the formula for percent composition is the mass of the element divided by the mass of the compound times 100. So let's put our part, or the mass of the element, on top, which is 159.808, and we're going to divide it by the mass of the whole compound, which is 223.354. And remember, we have to multiply that by 100 because it's percent composition and we want a percent. So when we do that, we're going to get 71.549%. And there's your answer right there. Okay, now you try it. Here's a sample ACP question. What is the percent composition by mass of calcium in calcium hydroxide? Good luck with that. Well, students, that's the end of our Thanksgiving review. Good luck in completing this, and we just want to say have a happy Thanksgiving.